Welcome to this organic chemistry tutorial. And in this tutorial we are going to discuss about nucleophilic substitution reactions. Mechanistically there are three types of nucleophilic substitution reactions: SN1, SN2 and SNI. This is the scope of our syllabus. Alkyl halides, nucleophilic substitution reactions, SN1, SN2, SNI, mechanisms with stereochemical aspects and factors affecting nucleophilic substitution reactions. First we will discuss the mechanism of SN1 reactions. SN1 stands for Substitution Nucleophilic Unimolecular, and the reaction is described by a reaction rate law which looks like this. Contrary to the popular belief or the popular saying that states that the mechanism of SN1 reaction is such that it follows first order kinetics, it is important for one to understand that the mechanism is implied from the kinetics of the reaction, and the experimentally observed kinetics of this reaction stood as rate proportional to concentration of only the alkyl halide and not the concentration of the nucleophile. Based on this rate law, the mechanism which was suggested was a two-step mechanism. The first step involving a slow loss of the leaving group, generating a reactive intermediate called as the carbocation. And as the second step, which is a fast step, there is a rapid attack of the nucleophile on the carbocation so as to generate the product. The energy profile diagram of this reaction looks somewhat like this, with two transition states and an intermediate, the intermediate being the carbocation. This multi-step reaction has an intermediate and two transition states, and in SN1 reaction there is a loss of a leaving group which generates an intermediate carbocation, and the loss of the leaving group is very, very important driving force towards exhibition of this reaction mechanism, which is SN1 type. Based on the proposed mechanism, we can enlist various factors that affect the SN1 reaction. And one of the major factors which affect SN1 mechanism is the structure of the substrate. And if you look at the reactivity order of the substrate, a tertiary halide reacts fastest in an SN1 reaction as compared to a primary halide, and this has to do with stability of the carbocation so generated as an intermediate during SN1 reactions. If you see the relative rates of hydrolysis of these substrates, it appears as if the tertiary halide reacts almost 10 to the power 8 times faster as compared to a primary halide in an SN1 reaction. The second very important factor is the leaving group ability. Since the first rate determining step involves the bond breaking between the carbon atom and the leaving group, it's very important for the leaving group to be good so as to facilitate formation of the carbocation. Better leaving groups will make sure that the SN1 reactions are faster, whereas poor leaving groups will trigger the reaction in an SN2 or an alternate reaction pathway but not facilitate the SN1 mechanism. The third factor which affects nucleophilic substitutions are the strengths of the nucleophile. Nucleophilic strength, however, does not play a very important role in SN1 reaction. This is because the nucleophile appears in the second step of the mechanism, which is not the rate determining step. And hence often for SN1 mechanisms, nucleophile strengths are observed to be low. So you see solvolysis reactions typically which are performed with SN1 mechanism. So the solvolysis reactions, in specific terms, when the solvent is water, then it is called as the hydrolysis reaction, and the hydrolysis reaction is carried forward in the presence of water and not nucleophilic OH- when you want the reaction to go through the SN1 mechanism and not the SN2 mechanism. The next most important factor of substitution nucleophilic reactions which has to be borne out is the stereochemistry of the reaction. Whenever there is an asymmetric carbon atom on which nucleophilic substitutions are are held, what happens to the resultant stereochemistry will depend upon which mechanism is undertaken by the reaction. If the reaction follows an SN1 kind of a pathway, the SN1 mechanism forms a carbocation as an intermediate. The carbocation has sp2 hybridization of the central carbon atom on which nucleophilic substitution is aimed, and therefore the carbon atom is planar. Due to its planarity, there is an equal likelihood of the nucleophile to attack either from the rear or from the front side, generating products in equal proportions, which are both mirror images of one another, and hence they are both enantiomers. Due to this reason, SN1 reaction often promotes racemization. On the other hand, SN2 mechanism, when we come to it, will lead to inversion of configuration. So stereochemical evidences are very important in ascertaining whether the reaction mechanism being followed is SN1 type or SN2 type. Though it is mechanistically implied that the SN1 reaction should involve racemization, complete racemization, most of the times experimentally there is often 5 to 20% inversion which is observed, and this inversion is accounted for by formation of ion pairs. So the first step, which is a slow step of dissociation of an alkyl halide to the constituent cation and the counter ion, does not happen in a single step, but it is multi-step. In that, it first forms an intimate or a contact ion pair or a tight ion pair, followed by the intimate or the contact ion pair, which is represented by 16 in the image, is the loose or solvent separated ion pair, which is represented by 17 in the picture. Eventually, as the solvent pulls apart the two ions, it leads to the formation of free ions. Now, if the free ions are the ones that undergo attack by the nucleophile and the carbocation has got fully generated, then there is perfect racemization which is observed. However, with differing degrees of nucleophilic attack on 18, 17 and 16, there would be a marginal amount of inversion which will predominate over retention of configuration, because in a tight ion pair, the accessibility of the nucleophile from the opposite side is going to be better as compared to the same side where the tight ion pair has been established. So that's how in the ion pair theory, it explains that based on where exactly at what moment the nucleophilic attack takes place from the free alkyl halide to the completely separated alkyl halide tells us where which type of stereochemistry should predominate, and hence in SN1 reactions as well, complete racemization is often not observed based on the ion pair effect. The last important factor which affects nucleophilic substitution is the polarity of the solvent. And the solvent polarity affects the rate of SN1, SN2 and other nucleophilic substitution reactions based on stabilization of the transition state or stabilization of the reactants. So it all depends on whether the reactants are more charged or whether the intermediate or the transition state is more charged. So if the charges are dispersed as we go from the alkyl halide to the intermediate, then on increasing the polarity of the solvent, the rate of the reaction will decrease. Any factor that increases the stability of the intermediate or the transition state will lead to an increase in the rate of the reaction. And polar solvents will tend to stabilize polar species, and since the intermediate involved in SN1 reactions are carbocations, and carbocations have a net unit positive charge on them, the intermediate is stabilized due to polarity of the solvent, and hence rates of SN1 reaction are often increased by huge factors as you go from non-polar to polar solvents. To summarize, we've discussed SN1 reaction, its mechanism which involves two steps. In the first one, in generation of the carbocation, which is a slow step, and in the second step, attack of the nucleophile to the carbocation generated. So discussed kinetics of this reaction, which does true justice to its nomenclature being unimolecular, and that unimolecular term comes from the kinetics of the reaction, which proves that the reaction is of following first order kinetics. We discussed stereochemistry of the reaction, which was earlier only popularly known as racemization, but now we know that there is some extent of inversion of configuration which predominates due to ion pair effect, which is something which is new. Then we also discussed factors affecting SN1 reaction, primarily the substrate. So a tertiary substrate is likely to undergo SN1 reactions as compared to a primary substrate. The strength of the nucleophile strength required for SN1 reactions are low as against SN2 reactions, which is one compare and contrast between the two. The solvent polarity, polar solvents tend to stabilize the intermediate carbocation being formed and hence increase the rate of SN1 reaction, and the leaving group ability, which is fundamental towards establishing the mechanism of the reaction as SN1. Thank you.